In the late 20th century, astronomers aimed their telescopes toward dying stars and expected to watch the universe slowing down. Instead, the light returned with a far stranger message. Cosmic expansion is accelerating. Something unseen is stretching the distance between galaxies, while another invisible presence surrounds those galaxies, bending light and holding stars in their orbits. Together, dark matter and dark energy appear to shape almost the entire cosmos, yet neither has ever been directly understood. This journey follows the hidden gravity discovered in galaxy clusters, the silent halos traced by Vera Rubin, the accelerating universe revealed by distant supernova, and the unsettling possibility that empty space itself carries energy. A like subscription or thoughtful share helps this quiet exploration travel farther. Sincere thanks go to everyone spending this time beneath the mystery of the universe. A comment sharing the local time and listening location is always warmly welcomed. Now, the visible stars begin to fade, and the journey into the dark universe begins. For most of the 20th century, the expansion of the universe seems to carry a simple expectation. Space is growing, galaxies are drifting apart, and gravity should gradually slow the motion. Every star, every cloud of gas, every galaxy, and every unseen mass should pull against the expansion, adding a faint cosmic resistance. The farther the universe stretches, the more that resistance should reveal itself through careful measurement. By the early 1990s, 2 international teams of astronomers set out to measure that slowing with greater precision than ever before. One becomes known as the High Z Supernova Search Team. The other is the Supernova Cosmology Project. Their purpose is not to discover a new force or a hidden form of energy. Their purpose is to weigh the universe by watching its expansion lose speed. To do this, they turn toward some of the brightest events in nature, the explosions of dying stars known as Type I supernovae. These supernovae arise when a white dwarf, the dense remnant of a star, undergoes a catastrophic thermonuclear disruption. For a brief time, a single explosion can shine with the light of an entire galaxy. More importantly, these events possess a useful regularity. Their true brightness can be estimated from the shape of their fading light, allowing astronomers to compare how bright they appear with how bright they actually are. That comparison reveals distance. In this way, each supernova becomes a marker in the deep past, carrying information across billions of years. The light arriving at a telescope does not show the universe as it is now. It shows the universe as it was when the light began its journey. A nearby supernova records a more recent stage of cosmic history. A distant one records a much earlier stage. By collecting many such events at different distances, astronomers can reconstruct the changing pace of expansion through time. The method is delicate. A distant supernova is faint, brief, and easy to miss. The sky must be searched repeatedly, with fresh images compared against earlier ones until a new point of light appears where none existed before. Once found, the supernova must be observed quickly before it fades. Its spectrum, the spread of its light into different wavelengths, must confirm its type. Its brightness must be corrected for dust, for the behavior of the explosion, and for the stretching of light caused by the expansion of space. Powerful telescopes on Earth and in orbit are brought together for this work. The Keck telescopes in Hawaii gather the dim light of remote galaxies. The Hubble Space Telescope observes above the blur of the atmosphere. Beneath all this effort rests a calm prediction. The universe begins in a hot, dense state and expands outward. Matter pulls on matter. Radiation also contributes to gravity. Over time, this combined attraction should reduce the rate of expansion. The slowing may be slight or strong, depending on how much matter the universe contains. If the density is high enough, expansion might one day halt and reverse. If the density is lower, expansion may continue forever, but at an ever-decreasing pace. Either way, the expectation remains that gravity acts as a brake. The supernovae should reveal the strength of that brake. Yet as the observations accumulate, the distant explosions appear too faint. Their faintness means they are farther away than expected in a universe whose expansion is slowing. At first, the result does not look like a discovery. It looks like a problem. Astronomers search for mistakes because extraordinary conclusions can grow from ordinary errors. Perhaps the supernovae are not as uniform as believed. Perhaps distant explosions differ from nearby ones because the early universe contains different kinds of stars. Perhaps dust between galaxies dims the light without producing the usual reddening. Perhaps the telescopes introduce a bias. Perhaps the calculations mishandle the stretching of the spectrum. Each possibility offers a way for the familiar picture to survive. The teams repeat the analysis. They compare methods. They improve the calibration. They test whether hidden dust or changing stellar populations could imitate the signal. The result remains. The distant supernovae are still too faint. The expansion of the universe is not merely continuing, it is accelerating. This conclusion reverses the original purpose of the survey. The astronomers set out to measure how quickly the cosmos is slowing, and instead they find that it has begun to speed up. The change is not a local motion of galaxies through space. It is the expansion of space itself. On the larger scales, the distances between unbound galaxies grow more rapidly as time passes. Gravity still works. Galaxies still attract nearby galaxies. Stars remain bound inside galaxies, and planets remain bound to stars. Yet across the immense spaces between clusters and superclusters, another influence becomes dominant. It acts not like an ordinary push from a central location, but like a property spread throughout space. The more space there is, the more of this influence seems to be present. The discovery arrives quietly through repeated measurements, but its meaning is the cosmos contains something not included in the familiar inventory of matter and radiation. Whatever drives the acceleration does not shine. It does not absorb light in any obvious way. It does not gather into stars or clouds. It reveals itself through the changing geometry of the universe. Astronomers give it a practical name, dark energy. The name describes ignorance more than understanding. Dark means unseen and unknown. Energy means that it affects the dynamics of the cosmos. It does not yet identify a substance, a particle, or a mechanism. It marks the place where explanation ends and observation continues. The result also reshapes the cosmic balance. Ordinary matter, the atoms that form stars, planets, oceans, dust, and living cells, accounts for only a small fraction of the total content. Another larger share belongs to dark matter, an invisible source of gravity already inferred from galaxies and clusters. Dark energy appears to dominate both. The visible universe, bright with stars and galaxies, becomes only the thin luminous surface of a much deeper structure. Most of reality seems to reside in forms that no telescope can see directly. The supernova discovery does not stand alone for long. Other lines of evidence begin to support the same picture. The cosmic microwave background, the faint afterglow of the early universe, carries a pattern that reveals the geometry and composition of the cosmos. Large surveys chart the distribution of galaxies across immense volumes. The growth of cosmic structure depends on the competition between gravity and expansion. Together, these measurements point toward a universe in which dark energy becomes increasingly important as matter spreads thinly through expanding space. In the early universe, matter dominates because it is densely packed. Its gravity guides the formation of stars, galaxies, and clusters. As expansion continues, the density of matter falls. Dark energy, by contrast, appears not to thin away in the same manner. After billions of years, a threshold is crossed. Matter remains powerful on local scales, but dark energy begins to rule the universe as a whole. The expansion changes from slowing to speeding up. This transition happens long before the supernova light reaches Earth, and the distant explosions preserve the record. They are quiet witnesses to the moment when the cosmic balance shifts. The discovery earns Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, but the deeper reward is uncertainty. A measurement intended to complete the known picture instead opens a much larger unknown. Dark energy may be connected to the cosmological constant, a term once introduced into Einstein's equations. It may arise from the energy of empty space. It may involve a field that changes over time. It may indicate that gravity behaves differently across the greatest distances. None yet offers a complete answer. The calmest fact is also the strangest: the universe is speeding up, and the cause remains hidden. Across the dark between galaxies, space continues to widen. Remote light travels through an ever-changing cosmos, carrying clues from ages when the balance was different. The supernovae fade, their brief brilliance disappearing into the background, but the pattern they reveal remains. The universe does not expand like a stone thrown upward and slowed by gravity. It expands with a deepening motion, as though the emptiness itself participates. What first appears to be a correction in a distance chart becomes a doorway into the largest mystery in modern cosmology. The known universe is not only filled with invisible mass, it is also governed by an unseen influence that stretches the cosmic fabric faster with time, quietly carrying the most distant galaxies farther apart and drawing the future toward a darkness that has not yet fully arrived. Long before dark matter acquires its name, gravity begins to reveal that light itself can be bent by mass. The idea emerges from general relativity, Albert Einstein's description of gravity not as an invisible force pulling across empty space, but as a change in the shape of space and time. Matter tells space-time how to curve, and curved space-time tells matter and light how to move. A beam of light still follows the straightest possible path, yet in curved space the straightest path can appear bent. This prediction is subtle near an ordinary star, but the Sun provides a powerful test. During a total solar eclipse in May of 1919, teams led by Arthur Eddington and Frank Dyson travelled to observe stars close to the darkened edge of the Sun. Under normal conditions, the Sun's glare hides those stars. During the eclipse, their positions can be recorded and compared with photographs taken when the Sun lies elsewhere in the sky. If general relativity is correct, the Sun's gravity should shift the apparent positions of the stars by bending their light. The weather is poor, the equipment difficult, and the measurements demanding, yet the result supports Einstein's prediction. The starlight has moved by roughly the expected amount. Gravity has acted like a lens. At first, the effect seems more important as a test of theory than as a tool for astronomy. A star bends light only slightly, and the required alignment is rare. Einstein himself doubts that gravitational lensing will become useful in practice. The universe, however, contains structures far more massive than the individual stars. Galaxies contain billions of stars, clouds of gas, central black holes, and, as later evidence suggests, enormous quantities of invisible matter. Clusters of galaxies are larger still. Their combined gravity curves space so strongly that light from much more distant objects can be deflected, stretched, brightened, split, and sometimes wrapped into arcs or rings. The lens does not need glass. Space-time itself performs the work. This becomes important because gravitational lensing responds to total mass, not merely to matter that shines. A telescope records starlight and glowing gas, but gravity reacts equally to luminous and dark material. By studying how a foreground galaxy or cluster distorts the image of something behind it, astronomers can map mass that would otherwise remain unseen. The method is direct in one sense and indirect in another. No dark object appears on the detector. Instead, its presence is written into the altered path of light. The geometry of the distortion becomes a silent record of gravity. A perfect alignment between a distant source, a foreground lens, and Earth can produce an Einstein ring, a circle of light around the lensing mass. A slightly imperfect alignment may form several images of the same source. Complex clusters stretch background galaxies into long, curved arcs. Even when the distortion is too small to notice in a single object, the shapes of thousands or millions of faint galaxies can be analysed statistically. Their slight common stretching reveals what is called weak gravitational lensing. This technique allows astronomers to trace the large-scale distribution of mass across wide areas of the sky. The importance of the effect becomes clear in the late 1970s with the discovery of a strange pair of bright objects. The 2 points appear close together and seem almost identical. Their spectra match. Their brightness changes in related ways. The explanation is not that two nearly perfect copies happen to sit side by side. They are two images of one distant quasar, produced because the gravity of a foreground galaxy bends the quasar's light along more than one path. A quasar is the intensely bright centre of a distant galaxy, powered by matter falling toward a supermassive black hole. Because quasars can be seen across immense distances, they provide ideal background beacons. Their light passes through large regions of the universe before reaching Earth, and any massive structure along the route can reshape the view. The double quasar turns gravitational lensing from an elegant prediction into a practical instrument. Soon, more lenses are found. Some show 2 images, some 4, some rings, and some broad luminous arcs around clusters. Each one offers a way to weigh the foreground structure. The more strongly light is bent, the more mass must be present. Repeatedly, the mass inferred from lensing exceeds the mass visible in stars and gas. The conclusion agrees with the motions of galaxies, but it arrives through an entirely different path. Galaxies may move too quickly because unseen matter holds them in orbit. Light may bend too strongly because unseen matter curves the space it crosses. The same invisible component explains both. This convergence matters. A single puzzling observation can be blamed on uncertain measurements or incomplete models. Several independent effects pointing to the same hidden mass are much harder to dismiss. Gravitational lensing also reveals where the mass is located in a cluster. Bright galaxies mark some of the structure, while hot gas fills the space between them and glows in X-rays. Lensing maps often show that the greatest mass concentration does not always coincide with the brightest gas. This becomes especially striking when clusters collide. The galaxies, separated by enormous distances, mostly pass through one another. The hot gas clouds collide, slow down, and remain nearer the centre. The dominant gravitational mass traced through lensing can continue forward with the galaxies rather than staying with the gas. Such systems suggest that most of the mass is not ordinary atomic matter. It behaves like a nearly collisionless substance, interacting strongly through gravity while passing through itself with little resistance. The famous bullet cluster becomes one of the clearest examples, though it is not the only one. Its value does not rest on a single dramatic image, but on the separation between different components. X-ray observations show the shocked gas. Optical images show the galaxies. Lensing measurements reveal where most of the mass lies. These maps do not align. Ordinary matter gathers mainly in the slowed gas, while the gravitational mass is displaced. The pattern is difficult to explain by visible matter alone. It indicates that an additional component carries most of the gravity and moves differently from the gas. Lensing therefore does more than confirm missing mass. It begins to describe the behavior of that mass. It suggests something widespread, massive, cold in the sense of moving slowly compared with light, and weakly interactive except through gravity. Yet the method has limits. A lensing map reveals where gravity is strong, but it does not identify the particles responsible. It measures effects rather than composition. A map of invisible mass can be drawn with remarkable precision, while the nature of the mass remains unknown. This is one of the quiet paradoxes of modern cosmology. The universe can be weighed without being fully understood. Gravity provides an outline, but not a name. Across the sky, clusters become natural telescopes. Their gravity magnifies galaxies so distant that they would otherwise remain beyond detection. The same hidden mass that conceals itself also enlarges the ancient universe behind it. Very remote galaxies appear as thin red arcs, their light stretched by cosmic expansion and bent by intervening matter. Astronomers use these magnified images to study early star formation and young galaxies, while the distortions simultaneously refine maps of the lensing cluster. The unknown becomes an instrument for exploring another unknown. On larger scales, weak lensing surveys measure the accumulated bending caused by all the matter between distant galaxies and Earth. Tiny changes in apparent shape combine into a broad pattern known as cosmic shear. This pattern traces the invisible framework of the cosmic web, including filaments and dense knots where galaxies gather. The maps resemble a landscape seen only through its effect on passing light. Bright galaxies rest within it, but they do not account for most of its mass. The deeper structure is dark. General relativity, first tested with starlight passing beside the sun, becomes a method for charting that darkness across billions of light years. The connection spans almost the entire history of modern cosmology. An eclipse proves that gravity bends light. A double quasar shows that galaxies can form multiple images. Giant arcs reveal the immense mass of clusters. Weak lensing maps the hidden web between them. At every scale, the lesson remains calm and persistent. Light does not travel through an empty stage. It travels through a universe shaped by mass, much of which gives off no light of its own. The darkness is not blank. It has structure, weight, and geometry. It leaves no photograph of itself, yet every distorted galaxy carries its signature. Gravity turns the invisible into a pattern, and the pattern points toward a universe whose most abundant matter remains hidden behind the very curvature it creates. In the early 1930s, the universe is still becoming larger in the human mind. Only a short time has passed since astronomers accept that the Milky Way is not the whole of creation, but one galaxy among many. Beyond it lie other spirals, other islands of stars, scattered across distances so great that their light has travelled for millions of years. Among the largest known gatherings is the Coma Cluster, a vast collection of galaxies in the direction of the constellation Coma Berenices. Through a telescope, the cluster appears as a dense field of faint smudges, each one an entire galaxy. To Fritz Zwicky, working at the California Institute of Technology, these galaxies offer more than a distant spectacle. They offer a way to weigh a structure too large for any scale. Zwicky is already known for bold ideas and a difficult temperament. His imagination moves easily toward violent stellar deaths, compact remnants, and the strange consequences of gravity. He helps introduce the word supernova for the catastrophic explosion of a star, and considers the possibility that such events leave behind neutron stars, objects packed with matter at astonishing density. His manner often pushes colleagues away, but his scientific instinct is unusually sharp. In 1933, he turns that instinct toward the motions of galaxies inside the Coma cluster. The reasoning is simple in outline. A cluster is held together by gravity. Its galaxies move through the shared gravitational field, orbiting within the combined pull of everything the cluster contains. If their speeds can be measured, then the amount of mass needed to keep them bound can be estimated. A light cluster allows only slow motion. A massive cluster can hold galaxies moving much faster. The same principle keeps planets in orbit around the Sun, though the Coma cluster is larger by an almost incomprehensible degree. Zwicky studies the shifts in the light of its galaxies. When a galaxy moves toward Earth, its spectral lines shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. These changes reveal speed along the line of sight. The galaxies in Coma are not drifting gently. Many are racing through the cluster at close to 1,000 kilometers each second. At those speeds, the visible galaxies should not remain together unless the cluster contains far more mass than their stars can provide. With only the luminous matter in the calculation, Coma should be unstable. Its galaxies should escape into intergalactic space, and the cluster should disperse. Yet Coma remains a coherent structure. Gravity is holding it together, but the source of most of that gravity cannot be seen. To estimate the missing mass, Zwicky applies a principle known as the virial theorem. In a gravitationally bound system that is settled into a broad balance, motions of its members are related to the total gravitational energy of the system. The theorem allows motion to serve as a measure of mass. The faster the galaxies move, the deeper the gravitational well must be. Zwicky's calculation suggests that the amount of mass in Coma greatly exceeds what is visible in its galaxies. The difference is not a small correction, it is enormous. He concludes that a large quantity of Dunkelmaterie, dark matter, must be present. The phrase is practical rather than mystical. It refers to matter that produces gravity but little or no detectable light. Perhaps it consists of faint stars, cold gas, dead stellar remnants, or something not yet imagined. Zwicky cannot know its composition. He can only see the imbalance between motion and light. The cluster behaves as though it contains a hidden reservoir of mass. The conclusion is startling because astronomy is built around light. Telescopes collect photons, and almost every object in the sky is known through the radiation it emits, reflects, or absorbs. Zwicky's argument suggests that the dominant component of a great cosmic structure may not participate in that luminous exchange. The galaxies visible on a photographic plate may be only markers embedded within a much larger unseen system. The true cluster may extend beyond the bright points, forming a gravitational body whose substance remains dark. Yet the idea does not transform astronomy at once. It settles quietly into the literature. Several reasons contribute to the silence. The measurements are difficult and uncertain. Distances to galaxies are poorly known. The amount of light converted into an estimate of stellar mass depends on assumptions about the stars within each galaxy. Some intergalactic gas may be present but invisible to the instruments of the time. The Coma cluster may not be perfectly settled, which complicates the use of the virial theorem. Zwicky's own abrasive personality does little to encourage careful attention from colleagues. His conclusion seems too large, his evidence too remote, and the available tools too limited. Astronomy turns instead toward other great questions. The expansion of the universe demands measurement. The lives and deaths of stars are being reconstructed. Radio astronomy opens a new window on the sky. The missing mass in Coma remains an unresolved note at the edge of the field. For decades, it is possible to regard the problem as a peculiarity of one cluster or as a flaw in the early data. Later observations, however, make that dismissal harder. Other clusters show similar behavior. Their galaxies move too quickly to be held by visible matter alone. Hot gas discovered between the galaxies reaches temperatures of millions of degrees. This gas emits X-rays and adds substantial ordinary mass to the clusters, but not enough. It too requires a deep gravitational well to remain confined. Without additional mass, the hot gas should escape. Instead, it fills the cluster like a glowing atmosphere, held in place by gravity from something more extensive than the stars and gas together. Gravitational lensing eventually supplies another measure. Background galaxies appear distorted by the cluster's curvature of spacetime. The strength of the distortion again indicates far more mass than the luminous inventory contains. Motions, hot gas, and bent light all begin to tell the same story. Zwicky's forgotten clue is not fading, it is multiplying. The coma cluster becomes one early doorway into a universe whose visible parts do not control most of its gravity. Its galaxies are not the whole structure, but bright particles moving inside a vast dark halo. This changes the meaning of a cluster. It is no longer simply a crowd of galaxies gathered close together. It is a single gravitational system dominated by an unseen component that surrounds and binds them. The luminous galaxies trace the dark potential, much as leaves on water reveal a current that cannot itself be seen. Their speeds describe the depth of the hidden field. Their continued presence proves that something prevents escape. The mystery also reaches beyond coma. If clusters require dark matter, then the mass of the universe may be far greater than the light of the universe suggests. Cosmic accounting based only on stars becomes unreliable. Darkness is no longer merely the absence of objects between points of light. It may contain the principal substance shaping the motion of those points. This possibility remains difficult to accept because no particle has been detected and no dark cloud has been photographed. The evidence is gravitational, and gravity is patient. It does not identify what creates it. It only reveals how strongly mass acts. Zwicky's result therefore carries a peculiar kind of certainty. The calculation can show that something is missing while offering almost no guidance about what the missing thing is. A new component enters cosmology not through direct sight, but through the failure of visible matter to explain motion. The coma galaxies continue their rapid paths, each one moving through a field much stronger than its neighbours can visibly produce. Their orbits become a message written across hundreds of millions of light years. The message waits through years of doubt until better instruments, new methods, and independent observations make it harder to ignore. What first appears to be an eccentric claim from an isolated scientist becomes the earliest clear sign that much of the universe may exist outside the reach of ordinary light. Modern measurements revise the scale of Zwicky's first estimate because distances, stellar populations, and cluster dynamics become better understood, yet they do not erase the central discrepancy. The exact ratio changes. The need for unseen mass remains. This distinction matters. Science does not preserve every early number, but it can preserve the structure of an argument when later evidence strengthens the same conclusion. In the quiet between the galaxies, an unseen mass is already holding the larger structures together, and the darkness begins to acquire weight. By the middle of the 20th century, galaxies are no longer distant smudges of uncertain nature. They are recognized as immense systems of stars, gas, dust, and gravity, each one turning slowly through space. Spiral galaxies seem especially orderly. Their bright disks curve into arms, their central regions glow with crowded stars, and their outer edges fade into darkness. The pattern suggests a simple comparison with the solar system. Near the center, Where most of the visible mass appears concentrated, gravity should be strongest. Farther out, gravity should weaken, and stars should move more slowly. Planets follow this rule around the Sun. Mercury travels quickly along its tight orbit, while Neptune moves far more slowly at the edge of the planetary system. A spiral galaxy should display a similar decline in orbital speed. Yet when astronomers begin to measure those speeds with care, the expected decline is missing. Vera Rubin becomes one of the central figures in this quiet overturning of the familiar picture. Working with instrument maker and astronomer Kent Ford, she studies the rotation of large spiral galaxies. Her path into astronomy has not been simple. The field is still shaped by assumptions about who belongs in observatories and who does not. Opportunities are restricted, institutions resist change, and even practical details such as access to telescope facilities reveal a world designed almost entirely for men. Rubin continues regardless. Her approach is patient, precise, and rooted in observation. She's not searching for a dramatic new substance. She's trying to understand how galaxies move, to measure that motion. Rubin and Ford examine the spectra of stars and glowing gas across galactic disks. A rotating galaxy does not move as one solid object. One side turns slightly toward Earth while the other turns slightly away. The light from the approaching side shifts toward shorter wavelengths, while the light from the receding side shifts toward longer wavelengths. By measuring those shifts at different distances from the center, astronomers can build a rotation curve, a simple graph showing orbital speed across the galaxy. The expected curve rises near the center, where the enclosed mass increases rapidly, and then falls in the outer regions, where visible matter becomes sparse. The observed curve does something else. It rises and then remains nearly flat. Stars and gas far from the bright center move almost as quickly as material much closer in. The outer galaxy does not slow down. This is not a small irregularity at one location. The same pattern appears across many spiral galaxies. Their visible disks fade, but their rotational speed remains high. If only the observed stars and gas provide gravity. The outer material should not remain bound at those speeds. It should drift away into intergalactic space. The fact that it stays in orbit means the gravitational field extends well beyond the luminous disk. Something massive surrounds the galaxy. The visible spiral rests inside a much larger, darker structure. This structure becomes known as a dark matter halo. The word halo does not imply a bright ring. It describes a broad, roughly spherical distribution of unseen mass, enclosing the flattened disk of stars. In many galaxies, the halo appears to contain several times more mass than all the visible matter combined. Its gravity dominates the outer regions, holding fast-moving stars and gas in place. The galaxy seen in photographs is therefore not the full galaxy. It is the luminous center of a much larger gravitational system. The dark halo may extend far beyond the last visible stars, fading gradually into intergalactic space. Rubin's measurements are powerful because they bring the missing mass problem from rare clusters into individual galaxies. Zwicky's Coma cluster lies hundreds of millions of light-years away and contains thousands of galaxies moving in a complex environment. A critic can wonder whether the cluster is disturbed, whether the measurements are incomplete, or whether the theory of its internal balance has been applied too simply. Spiral galaxies provide a cleaner test. Their rotation can be traced point by point. The same discrepancy appears repeatedly. Visible matter cannot explain the motion. The evidence also reaches beyond the optical disk. Neutral hydrogen gas often extends farther than the starlight and emits radio waves at a distinctive wavelength. Radio telescopes can follow this gas into regions where few stars are visible. There, at the dim edge of the galaxy, the rotation curve often remains flat. the farther the observations reach. The more clearly the unseen mass reveals itself. Darkness is not merely filling gaps between bright features. It is controlling the motion where the light has almost disappeared. Alternative explanations are considered. Perhaps there are large populations of faint stars, cold planets, stellar remnants, or clouds of gas that ordinary telescopes fail to detect. Some hidden ordinary matter certainly exists. Galaxies contain dim stars, compact objects, and cold material. Yet there are limits to how much ordinary atomic matter the universe can contain. The abundance of light elements formed in the early universe constrains the total amount of normal matter. Later measurements of the cosmic microwave background reinforce that limit. The unseen mass required by rotation curves is too abundant to consist entirely of ordinary atoms. The halos seem to be made mostly of something else, something that does not emit, absorb, or scatter light in the usual way. The shapes of rotation curves also reveal how this mass is distributed. If all matter were concentrated toward the center, orbital speeds would fall with distance. Flat curves mean the amount of enclosed mass continues to grow as the measurement moves outward. The dark halo must be extended. Its density decreases with distance, but its volume increases so greatly that more and more mass lies inside larger orbits. A star in the outer disk therefore feels the pull not only of the bright center, but of an enormous surrounding reservoir. This picture changes the nature of a spiral galaxy. The graceful arms, glowing clouds, and central bulge become a small luminous pattern embedded in a dark gravitational sea. Dark matter does not determine every detail. Gas pressure, stellar winds, magnetic fields, supernova explosions, and central black holes all shape galaxies. Yet the halo sets the broad conditions within which these processes unfold. It determines how much material can be held, how quickly the disk turns, and how the galaxy responds to encounters with neighbors. Rubin's work does not stand alone. Other astronomers measure similar curves using different instruments and wavelengths. Dwarf galaxies, with relatively few stars, often appear even more dominated by dark matter. Large spirals reveal extended halos through the motion of gas, satellite galaxies, and stellar streams. Elliptical galaxies, though harder to analyze because their stars move in many directions, also require unseen mass. Across the diversity of galaxies, the same gravitational excess returns. Not every system behaves identically, and the distribution of dark matter remains a subject of active study. But the broad conclusion becomes difficult to escape. Most galaxies contain much more mass than their light suggests. This realization also strengthens the idea that dark matter is not a rare collection of hidden objects. It is a universal component of cosmic structure. Every large galaxy seems to carry an invisible envelope. Clusters contain still larger reservoirs. The universe begins to look layered, with ordinary matter gathered inside a dominant dark framework. The visible stars trace only the regions where gas has cooled enough to ignite. The halo itself remains unlit. Rubin is careful in how she interprets the evidence. Observation establishes the need for additional gravity, but it does not identify the source. A new kind of matter is one explanation. A failure in the understanding of gravity is another. Yet any alternative must reproduce the same flat rotation curves across many galaxies, while also accounting for clusters, lensing, the cosmic microwave background, and the growth of structure. As evidence accumulates, dark matter becomes the simplest shared explanation, even though its composition remains unknown. The mystery, therefore, deepens in an unusual way. The existence of the effect becomes clearer while the nature of its cause remains hidden. A galaxy can be mapped with increasing precision, its stars counted, its gas traced, and its speed measured across tens of thousands of light years, yet most of its mass refuses to appear. The bright spiral turns inside an unseen halo that may be several times wider than the luminous disk. Each outer star follows a path shaped by matter it never touches and never illuminates. Rubin's rotation curves transform dark matter from an old cluster puzzle into a central fact of galactic astronomy. The curves are simple, almost calm in appearance, but their flatness carries a profound message. The universe does not reveal its mass through light alone. Galaxies are held together by a hidden architecture, and the deeper the measurements reach into their fading edges, the more firmly that architecture takes control. On the larger scales, the universe is not arranged like a random scattering of lights. Galaxies gather into groups, groups gather into clusters, and clusters connect through immense filaments that stretch across regions almost too large to picture. Between them lie vast voids where comparatively few galaxies form. This pattern is called the cosmic web. It resembles a network of threads and knots spread through space, though the likeness is only a guide. Its existence raises a deep question. If the early universe begins in a hot and nearly smooth state, how does such elaborate structure appear? The answer begins with tiny differences in density. In the earliest moments, matter is distributed with extraordinary uniformity, but not perfect uniformity. Some regions contain slightly more matter than average, while others contain slightly less. These differences are minute, yet gravity acts patiently. A region with a small excess of mass exerts a slightly stronger pull. More matter drifts toward it, making the region denser and strengthening the pull still further. Over long spans of time, this quiet imbalance grows. Dense regions become denser. Sparse regions lose material. The first faint pattern deepens into a web. Ordinary matter participates in this growth, but by itself it cannot easily build the observed universe quickly enough. In the young cosmos, normal matter exists mainly as hot gas and remains strongly coupled to radiation for hundreds of thousands of years. Light presses against it and resists collapse. Dark matter behaves differently. It does not interact with light in the usual way, so radiation cannot hold it back. While ordinary matter remains trapped in the bright early plasma, dark matter begins to gather under gravity. It falls into the small density ripples and forms a hidden framework before atoms can move freely. When the universe cools enough for electrons and atomic nuclei to combine, light finally travels through space without constantly scattering. Ordinary gas is released from the grip of radiation and begins to fall into the gravitational wells already prepared by dark matter. The unseen component has started the work in advance. It becomes the scaffold around which visible structure forms. This is why dark matter is often described as cold. The word does not mean that every particle has a low temperature in the everyday sense. It means that dark matter moves slowly compared with light during the era when cosmic structure begins to grow. If it moved too quickly, it would stream out of small, dense regions and erase the fine pattern needed to form galaxies. Cold dark matter remains clumped enough for gravity to build structure from small scales upward. Small halos form first. They merge into larger halos. Gas gathers within them, cools, and eventually produces stars, over time. The earliest galaxies appear as luminous islands inside deeper concentrations of darkness. These young systems collide and combine. Their halos merge, their gas is compressed, and their stars are rearranged. Larger galaxies grow from many smaller pieces, while clusters form where several filaments meet. This process is called hierarchical growth because structure develops through repeated assembly. The smallest bound systems emerge early, and larger systems appear through gradual merging. Computer simulations make this slow construction visible. Astronomers begin with a model of the early universe containing tiny density variations, like those measured in the cosmic microwave background. They add the known laws of gravity and allow the virtual universe to evolve. At first, the matter appears almost smooth. Then faint threads emerge. The threads thicken. Dense knots form where filaments cross, halos gather, merge, and grow, when ordinary gas and the physics of stars are included. Galaxies ignite within the dark network. The resemblance between these simulated universes and the observed cosmic web is one of the strongest successes of the dark matter model. Surveys of real galaxies reveal clusters, walls, filaments, and voids arranged in patterns that closely match the structures produced in simulations containing cold dark matter. The Sloan Digital Sky Survey and earlier redshift programs turn the sky into a three-dimensional map by measuring both the position and the recession speed of galaxies. As the maps expand, the universe begins to resemble a sponge or a branching root system, with bright concentrations surrounding great empty regions. These surveys trace the luminous part of the web, but the galaxies are only markers. The majority of the mass lies in dark matter spread through halos and filaments. Weak gravitational lensing offers a way to map this hidden layer more directly. The shapes of distant galaxies are subtly distorted by all the matter their light passes on the way to Earth. When many such distortions are combined, broad maps of invisible mass emerge. The luminous galaxies tend to gather where the lensing signal is strongest, confirming that they sit within a larger dark structure. Yet the match is not perfect at every point. Gas can be blown outward by stellar explosions. Galaxies can move within halos. Collisions can separate visible and dark components. The web is therefore not a simple drawing in which light and mass overlap exactly. It is a layered structure in which dark matter provides the broad framework while ordinary matter responds through cooling, heating, pressure, radiation, and chemistry. The role of dark matter is especially clear in the formation of the first galaxies. After the early universe becomes transparent, there is a long period before the first stars ignite. During this cosmic dawn, dark matter halos continue to gather gas. In the densest regions, gas cools enough to collapse into compact clouds. Gravity compresses these clouds until nuclear fusion begins, and the first stars bring light back into the universe. Without dark matter, this sequence would proceed far more slowly. Ordinary matter alone would struggle to collapse against its earlier interaction with radiation and the ongoing expansion of space. Dark matter gives gravity a head start. It creates the deep wells needed for gas to accumulate. The first light therefore appears inside structures that are already mostly dark. As stars form and die, they enrich the gas with heavier elements. Later generations of stars produce planets, dust, and complex chemistry. The visible richness of the universe unfolds within a framework that never shines. Dark matter does not build stars directly, and it does not determine every detail of a galaxy, but it creates the conditions that make large-scale structure possible. It influences where gas collects, where galaxies form, how clusters assemble, and how matter flows across cosmic time. Even the voids carry its signature. They are not perfectly empty, but they contain less matter because gravity has drawn material towards surrounding filaments and knots. Over billions of years, the contrast deepens. Dense regions become crowded with galaxies, while voids expand and grow emptier. Dark energy later accelerates this separation on the larger scales, but the original pattern is shaped by dark matter and gravity. The cosmic web also explains why galaxies are not evenly distributed. They appear in chains, sheets, and clusters because they follow the underlying dark matter. A galaxy is therefore both an object and a signpost. Its light reveals where ordinary matter has gathered, while its location hints at the hidden gravitational landscape around it. The Milky Way itself lies within one such network, part of a local group embedded in a larger region of filaments and flows. Its position is not isolated or accidental. It belongs to a hierarchy extending from the dark halo around the galaxy to the broad web of nearby clusters and beyond. This view transforms dark matter from a missing ingredient into a cosmic architect. Yet through that simple response, repeated across almost 14 billion years, it guides matter into the structure seen today. The universe gains complexity because tiny beginnings are amplified. A slight excess becomes a halo gathers gas. Gas forms stars. Stars gather into galaxies. Galaxies merge into clusters. Clusters connect through filaments. At every stage, the visible world grows inside an invisible foundation. The mystery becomes deeper because the effects of dark matter are now present almost everywhere. It does not merely rescue the motion of one cluster or explain the flat rotation of one galaxy. It appears woven into the entire history of cosmic structure. Remove it from simulations, and the universe fails to resemble the one observed. Keep it, and the great web naturally takes shape. Yet the substance itself remains unseen, detected through gravity but absent from every ordinary image. The universe seems to have been sculpted by something that leaves no light behind. Its work fills the sky, while its nature stays hidden in the dark between the galaxies. Dark matter becomes easier to describe through its effects than through its substance. It gathers around galaxies, binds clusters, bends light, and helps build the cosmic web. Yet none of these roles identifies what it is made from. The search, therefore, often advances by elimination. Each familiar form of matter is tested against the evidence. Some candidates explain a fraction of the missing mass. Others match one property but fail another. Slowly, the possible answer is pushed away from the known contents of the universe and towards something more elusive. One of the first serious candidates is the neutrino, a particle so light and unreactive that vast numbers pass through stars, planets, and living bodies almost without disturbance. Neutrinos are born in nuclear reactions, in radioactive decay, in stellar explosions, and in the hot conditions of the early universe. Their abundance is immense. They do not emit light, and they interact only through the weak nuclear force and gravity. At first, this seems promising. A particle that is everywhere, invisible, and difficult to detect appears well suited to the dark matter problem. The neutrino itself enters physics as an answer to missing energy. In certain forms of radioactive decay, the observed particles do not carry away all the expected energy. Rather than abandon the conservation of energy, Wolfgang Pauli proposes that another unseen particle escapes with the difference. The idea is later developed, and the particle is eventually detected. What begins as a hypothetical correction becomes a real member of nature. This history offers encouragement. Perhaps dark matter is another invisible particle waiting for a sufficiently sensitive experiment. Yet ordinary neutrinos fail as the dominant dark matter because they are too light and move too quickly. In the early universe, they travel close to the speed of light and stream out of small regions before gravity can gather them. Such fast dark matter is called hot dark matter. It tends to erase small density variations, allowing the larger structures to form first and smaller ones later. The observed universe develops in the opposite manner. Small halos and young galaxies appear early, while clusters and the broad cosmic web assemble through gradual merging. Cold dark matter fits this pattern far better. Neutrinos contribute a small amount to the cosmic mass budget, but they cannot provide the slow, clumping foundation required by galaxies. Ordinary atomic matter is the next broad possibility. Not all atoms shine. Cold hydrogen clouds can be dim. Small stars can be faint. Planets, comets, brown dwarfs, dead stars, and blackened remnants may hide in galactic halos. Collectively, such objects are often called massive compact halo objects. They possess gravity and may emit little light, so a galaxy filled with them could appear to contain dark matter. Astronomers search for these bodies through gravitational microlensing. When a compact object passes almost directly in front of a distant star, its gravity focuses the starlight and causes a temporary brightening. The lens itself may remain invisible, but its movement produces a characteristic rise and fall in the star's apparent brightness. Long observing programs monitor millions of stars in nearby galaxies, waiting for these rare events. Some are found, proving that dark compact objects exist. They include faint stars and stellar remnants scattered through galactic halos. Their numbers, however, are far too small. They cannot account for the full mass demanded by rotation curves and lensing maps. A deeper limit comes from the early universe. During the first few minutes after the beginning, conditions are hot and dense enough for the nuclei of light elements to form. The resulting amounts of hydrogen, helium, and traces of other light nuclei depend sensitively on the density of ordinary matter. Observed abundances therefore provide a cosmic inventory of atoms. The cosmic microwave background later offers an independent measurement of the same quantity. Both indicate that ordinary matter forms only a modest fraction of the total matter present. Much of the required dark matter cannot consist of hidden atoms, no matter how cold or faint those atoms become. The conclusion separates two ideas that once seemed almost identical. Dark matter is not merely ordinary matter that happens to be dark. It appears to be mostly non-baryonic, meaning it is not made from the protons and neutrons that build atomic nuclei. This leaves black holes. A black hole is genuinely dark in the most complete sense. Within its event horizon, escape becomes impossible, even for light. Black holes possess mass, interact through gravity, and can drift unseen unless they feed on surrounding material or influence a nearby object. Stellar black holes form from the collapse of massive stars, but their abundance is limited by the number of stars that can create them. Like other stellar remnants, they are made from ordinary matter and remain constrained by the cosmic inventory of atoms. They may contribute some hidden mass, but not enough to dominate the universe. Primordial black holes offer a more unusual possibility. These objects would not form from stars. They could arise from unusually dense regions in the very early universe, collapsing under their own gravity before galaxies or even atoms exist, because they form before ordinary nuclear matter takes its familiar shape. They may avoid some of the limits that restrict stellar black holes. Their possible masses span a vast range, from smaller than an asteroid to many times the mass of the Sun. If the right number forms in the right mass range, primordial black holes could behave like dark matter. Yet observations steadily narrow the available space. Small black holes would lose mass through Hawking radiation and may already have evaporated. Larger ones can bend and magnify starlight, disturb wide stellar systems, heat star clusters, alter the cosmic microwave background through accretion, or produce too many gravitational wave events. Each effect places limits on how common they can be. Microlensing surveys rule out many mass ranges as the sole explanation for dark matter. Other astronomical observations close additional gaps. Primordial black holes remain possible as a partial component in some ranges, but current evidence does not support a simple picture in which all dark matter consists of one broad population of black holes. The same pattern repeats with each familiar candidate. Cold gas exists, but not in sufficient quantity. Faint stars exist, but not in sufficient quantity. Neutron stars and white dwarfs exist, but their formation leaves chemical and luminous traces that limit their abundance. Neutrinos are abundant but too fast. Black holes are dark but constrained by how they form and how their gravity reveals them. None can supply the entire hidden framework required by galaxies, clusters, lensing, and the cosmic web. The search becomes less comfortable because the remaining answer may belong to physics beyond the known particles of ordinary matter. Yet elimination is not failure. It sharpens the profile of the unknown. Dark matter must survive for billions of years. It must carry mass. It must gather gravitationally and move slowly enough to form small structures early. It must interact weakly with light, or not at all. It must not collide strongly with ordinary matter, since dark halos pass through stars and gas without obvious friction. It may also interact only weakly with itself, though cluster collisions continue to refine that limit. These requirements form a quiet boundary around the mystery. The substance remains unseen, but its allowed behavior becomes increasingly precise. There is also an important caution. Astronomy rarely rules out a candidate in every possible form. A small fraction of dark matter may still consist of neutrinos, compact objects, or primordial black holes. The universe can contain several dark components at once. The central conclusion is narrower and stronger none of the familiar candidates, by itself, explains the dominant dark matter inferred across cosmic scales. This leaves open the possibility of an entirely new particle, a hidden sector of physics, or a revision to gravity. The process of exclusion therefore pushes the question deeper rather than closing it. Dark matter is no longer simply what telescopes fail to see. It is what remains after visible matter, faint matter, fast particles, and dark compact objects have each been measured and found insufficient around every galaxy. The invisible halo persists. Across every cluster, the missing gravity remains. The known universe supplies many dark things, but none yet matches the darkness that holds the cosmos together. Each failed candidate leaves the hidden mass more sharply defined, while the central question remains untouched beneath the growing weight of evidence. Once ordinary matter, fast neutrinos, and most compact objects fail to explain the hidden mass, the search turns inward, away from galaxies and toward the subatomic world. The standard model of particle physics describes the known building blocks of matter and the forces that act between them. Apart from gravity, it includes quarks, electrons, neutrinos, photons, gluons, and several other particles, all connected by a mathematical structure tested with extraordinary precision. Yet dark matter does not fit naturally inside it. The model contains no obvious particle that is stable, massive, electrically neutral, slow-moving in the early universe, and abundant enough to surround galaxies. This absence is not a minor inconvenience. It suggests that the dark matter problem may be evidence of a larger theory still hidden behind the known one. Particle physicists therefore begin to explore what lies beyond the standard model, and each extension creates new possibilities. One of the most famous candidates is the axion. It first appears not as an answer to cosmology, but as a solution to a puzzle involving the strong nuclear force. The equations allow a certain kind of asymmetry that experiments do not seem to observe. A proposed mechanism removes the unwanted effect, and the mathematics implies a new particle. The axion would be extremely light, electrically neutral, and very reluctant to interact with ordinary matter. A single axion would contribute almost no mass, but the early universe could produce enormous numbers of them. Together, they might form a cold, diffuse population that gathers around galaxies and influences structure through gravity. Their weakness is what makes them attractive and what makes them difficult to find. An axion could pass through a detector without leaving any trace. Experiments therefore rely on the possibility that, under carefully controlled conditions, an axion may convert into a photon in a strong magnetic field. Sensitive instruments search for the faint electromagnetic signal that such a conversion might create. Some listen for axions passing through Earth from the galactic halo. Others point toward the Sun, where axions might be produced in the hot interior. The expected signal is so delicate that ordinary heat, radio noise, and tiny instrumental effects can hide it. The search resembles listening for a single soft note beneath a storm of background sound. No confirmed detection has yet established axions as dark matter, but the candidate remains compelling because it emerges from an independent problem in physics and possesses many of the required cosmic properties. Another long-standing idea is the weakly interacting massive particle, often shortened to WIMP. Unlike the axion, a WIMP would be much heavier, perhaps comparable to an atomic nucleus or beyond. It would not carry electric charge and would interact only rarely with normal matter in the early universe. Such particles could be created and destroyed in great numbers. As the cosmos cooled and expanded, their collisions would become less frequent until a leftover population remained. Under broad assumptions, the predicted abundance can fall surprisingly close to the amount of dark matter inferred from astronomy. This coincidence becomes known as the WIMP miracle. Though it is not a proof, it is a hint that new particle physics near the energy scale of the weak nuclear force might naturally produce the right cosmic density. The WIMP idea becomes closely linked to supersymmetry, a proposed extension of the Standard Model. Supersymmetry pairs known particles with heavier partners. Quarks would have squarks, electrons would have selectrons, and particles that carry forces would gain their own companions. If the lightest supersymmetric particle is stable and neutral, it could survive from the early universe and behave as dark matter. The theory also promises to address other mathematical difficulties, which gives it influence far beyond cosmology. Yet its particle partners remain undetected. High-energy colliders have searched for signs that new particles are created in collisions and then escape unseen, carrying away momentum. No result has produced the clear pattern needed to confirm supersymmetry or a WIMP. Underground detectors pursue the same candidates from another direction. Earth moves through the Milky Way's dark halo. So dark matter particles should continually pass through the planet. Most would cross without interaction, but a rare collision with an atomic nucleus might produce a tiny recoil. Detectors are placed deep beneath mountains, mines, or ice to shield them from cosmic rays and ordinary radiation. Their target materials are cooled, purified, and monitored with extreme care. A single flash of light, a faint release of charge, or a slight vibration may indicate a collision. The difficulty is that natural radioactivity and neutrinos can create similar events. Years of observation produce increasingly strict limits, but no universally accepted dark matter signal. This silence does not prove that WIMPs do not exist. It shows that, if they exist within the tested mass ranges, they interact even more weakly than many early models predict. The allowed space narrows, and attention spreads toward other possibilities. Sterile neutrinos offer one path. Ordinary neutrinos interact through the weak force, but sterile neutrinos would avoid even that, communicating with known matter mainly through mixing with ordinary neutrinos and through gravity. If they are much heavier than familiar neutrinos and produced in the right way, they could move slowly enough to contribute to dark matter. They would not be fully cold in every model, so their influence on small galaxies and early structure becomes a crucial test. Astronomers also search for faint X-ray signals that might appear if sterile neutrinos decay over immense periods. Several disputed hints have drawn attention, but none has settled the question. Other candidates widen the field further, Dark matter might consist of extremely light fields spread smoothly through galaxies, behaving more like a coherent wave than a collection of separate particles. It might be made of heavier particles formed during violent transitions in the early universe. It could include objects known as dark photons, which resemble particles of light in a hidden sector. It might arise from asymmetric dark matter, where an imbalance between dark particles and antiparticles mirrors the imbalance that leaves ordinary matter after the early universe. Some ideas propose self-interacting dark matter. In that case, dark particles would collide with one another more readily than they collide with atoms. Such interactions might soften the dense centers predicted in some galactic halos and could help explain certain patterns in dwarf galaxies, though the evidence remains uncertain. The phrase hidden sector captures the growing possibility that dark matter is not a single isolated particle, but part of an entire unseen family. The known universe contains several kinds of matter particles, several forces, complex atoms, chemistry, stars, and life. There is no rule requiring the dark universe to contain only one simple ingredient. A dark sector might possess its own forces, bound states, radiation, or structures, all nearly invisible because they couple only weakly to ordinary matter. Gravity may be the one shared language between the two sectors. This idea is difficult to test because almost any additional interaction must remain subtle enough to have escaped detection. Yet astronomy can still constrain it. Colliding galaxy clusters show how freely dark matter passes through itself. Halo shapes reveal whether dark particles scatter. The cosmic microwave background records whether dark matter exchanges energy with radiation. Small galaxies preserve clues about how dark matter moves and clumps. Particle experiments, astronomical surveys, and cosmology therefore approach the same mystery from different scales. A detector beneath a mountain searches for one collision. A telescope studies a halo spanning hundreds of thousands of light years. A collider recreates brief high-energy conditions. A map of the early universe tests how unseen matter behaves across cosmic history. None of these methods alone is guaranteed to succeed, but together they narrow the possibilities. The search has become less like hunting for one predicted object, and more like exploring a landscape of theories. This widening can feel like uncertainty without progress, yet each failed experiment removes part of the landscape. Each null result tells physicists that dark matter is not as strongly interacting, not as massive, or not as simple as some models suggest. The mystery becomes more constrained even as it remains unsolved. Somewhere beyond the standard model may lie a particle or field that accounts for most of the matter in the universe. It may be light as a whisper, heavy as a hidden nucleus, or part of a dark world with its own internal order. For now, the known particle zoo stands illuminated by decades of experiments, while the dominant matter of the cosmos remains outside the cage, present through gravity, absent from every confirmed list. The mystery of dark energy begins long before astronomers give it a name. It begins inside the equations of general relativity, where gravity is no longer a force moving through space, but the changing shape of space-time itself. When Albert Einstein completes the theory in the second decade of the 20th century, he applies it not only to stars and planets, but to the universe as a whole. The equations do not naturally describe a cosmos that remains still. Matter curves space-time, and that curvature drives change. A universe filled with matter tends either to expand or to contract. Einstein, however, shares the common expectation of his era that the universe is eternal, static, and broadly unchanging. Stars may be born and die, but the cosmic structure itself is assumed to remain in balance. To preserve that picture, he adds a new term to the equations. This term becomes known as the cosmological constant. Its effect can oppose the attraction of matter across the larger scales, allowing a mathematical universe to remain suspended between expansion and collapse. The addition is not a separate substance in the ordinary sense. It is a property written into the geometry of space-time. In Einstein's model, it acts as a carefully chosen counterweight, strong enough to hold the cosmos still. The balance is delicate. A slight disturbance would cause expansion or contraction. But for a time, the static universe seems possible. Other physicists soon read the same equations differently. Alexander Friedmann finds expanding and contracting solutions without insisting on cosmic stillness. Georges Lemaitre later connects an expanding model with astronomical observations and with the idea that the universe may have begun in a denser state. The mathematics allows change from the beginning. The sky then supplies evidence. Galaxies beyond the Milky Way appear to recede, and the more distant they are, the faster that recession tends to be. The pattern is understood not as galaxies flying from one central explosion into empty surroundings, but as space itself expanding between widely separated systems. Once expansion becomes accepted, the original reason for the cosmological constant weakens. A term introduced to hold the universe static seems unnecessary. Einstein abandons the static model, and the constant largely retreats from the centre of cosmology. It never disappears from the equations. Mathematically, it remains permitted. Physically, many researchers simply set it to zero because observations do not seem to require it. For decades, cosmology advances without needing a repulsive cosmic component. The universe expands, but gravity is expected to slow that expansion. The future depends on the density of matter. If enough mass exists, the pull may eventually halt the growth and draw everything back together. If the density is lower, expansion may continue forever, though more slowly with time. In both cases, the movement remains governed by matter and radiation. The cosmological constant waits in the background, an unused possibility in the structure of the theory. By the late 20th century, astronomers begin measuring the expansion history with distant supernovae. Their goal is to determine how strongly the universe has decelerated. Instead, the explosions reveal that expansion has accelerated. The result creates a sudden need for exactly the kind of effect the discarded term can produce. A positive cosmological constant does not pull galaxies through space like a hidden wind. It changes the large-scale behavior of space-time. As the universe grows, matter becomes more thinly spread, and its average density falls. The cosmological constant, by contrast, represents an energy density that remains uniform as space expands. It does not dilute in the same way. Once matter thins enough, the constant begins to dominate the cosmic balance. Expansion then changes from deceleration to acceleration. An idea once used to prevent expansion returns as an explanation for expansion becoming faster. The irony is quiet but profound. The same mathematical term that once forces the universe to stand still can, with a different value and interpretation, drive it toward an ever more rapid separation. This return does not mean Einstein predicts dark energy in the modern sense. His purpose is different, and the observational discovery comes many decades later. Yet general relativity already contains a place where the new phenomenon can reside. The equations do not need to be rewritten from the beginning. A forgotten possibility simply becomes physically relevant. In the simplest modern model, dark energy is the cosmological constant. It is represented by an energy density belonging to empty space itself. Every region of space carries the same amount per unit volume. When space expands, more volume appears, but the density remains constant. This behavior sounds strange because ordinary substances thin as they spread. A cloud of gas becomes less dense when its volume increases. Radiation loses energy as its wavelengths stretch. Vacuum energy, if that is what the constant represents, does neither. Its total contribution grows as the universe creates more space. General relativity links energy density and pressure to the curvature of space-time, and the cosmological constant possesses a negative pressure. In everyday language, pressure pushes outward, while tension pulls inward. In cosmology, the sign enters the gravitational equations in a different way. Sufficiently negative pressure produces an effect that accelerates expansion. No galaxy feels a local gust. No force tears apart bound systems under present conditions. The effect becomes important only across enormous distances where the expansion of space can accumulate. Inside galaxies, gravity overwhelms it. Inside solar systems, it is negligible. Between distant clusters, over billions of years, it shapes the fate of the universe. The return of the cosmological constant also changes the cosmic inventory. Ordinary atoms account for only a small part of the total. Dark matter contributes a much larger share and provides most of the gravitational framework for galaxies and clusters. Dark energy appears larger still. The universe is therefore dominated by a component associated not with objects but with space. Stars, planets, gas clouds, and dark halos occupy the stage, yet the stage itself may control the final movement. This picture receives support from more than supernovae. The cosmic microwave background indicates that the geometry of the universe is close to spatially flat, while measurements of matter alone do not provide enough density to account for that flatness. A smooth additional component fills the gap. The distribution of galaxies and the characteristic scale left by sound waves in the early universe also trace the expansion history. The growth of clusters reveals how cosmic acceleration suppresses the formation of new large structures. Together, these observations converge on a model in which dark energy behaves very much like a cosmological constant. The model is remarkably successful, but success does not bring understanding. A constant can be placed in an equation and measured from the sky without revealing why it has its particular value. It can describe the acceleration while leaving its origin completely obscure. The measured value is tiny on the scales of particle physics, yet large enough to dominate the present universe. If it were much larger in the early cosmos, matter might have separated too quickly for galaxies to form. If it were negative and strong, the universe could have collapsed. Instead, it lies in a narrow range that allows stars, galaxies, and complexity to emerge before acceleration takes control. This coincidence invites explanation, but no agreed explanation exists. Some physicists treat the cosmological constant as a fundamental property of space-time, a number nature simply possesses. Others suspect that it reflects quantum vacuum energy, though calculations create an enormous mismatch. Still others consider that dark energy may not be constant at all, but a slowly changing field that only resembles one at the present epoch. Modified theories of gravity attempt to produce the same acceleration without a new energy component, yet each alternative must reproduce the broad success of the simplest model across supernovae, background radiation, galaxy surveys, and cosmic structure. For now, the cosmological constant remains the leading description because it fits so much with so little. Its simplicity is both reassuring and unsettling. The equations can accommodate it easily, but physics does not explain it. The term returns from the margins not as a completed answer but as a precise name for ignorance. Across the widening universe, matter thins, galaxies separate, and the constant influence of empty space becomes more important. Einstein's discarded counterweight no longer holds the cosmos still. It becomes the quiet driver of a future in which expansion continues to accelerate. carrying the most distant structures toward horizons from which their light will never return. Empty space appears simple only from a distance, between stars, between galaxies, and even between atoms. There seems to be almost nothing at all. Yet modern physics describes the vacuum not as a perfect absence, but as the lowest possible state of fields that fill the universe. Every known particle is associated with a field, and even when no particles are present, those fields do not become perfectly still. Quantum mechanics allows them to fluctuate. Energy can briefly appear in uncertain forms. Particle-like disturbances can emerge and vanish, and empty space retains a restless structure beneath all ordinary scales of observation. This quantum vacuum is not directly visible, but its effects can be measured in carefully controlled experiments. Two metal plates placed extremely close together experience a tiny attraction because the allowed quantum fluctuations between them differ from those outside. Atomic energy levels shift by small amounts that match calculations involving the vacuum. These results show that empty space has physical consequences. It is not merely a background in which matter exists. It participates in the behavior of matter itself. This makes the vacuum an obvious place to look for dark energy. A uniform energy belonging to space would naturally be present everywhere. It would not collect into galaxies or thin out as matter spreads. As the universe expands and creates more volume, the density of this vacuum energy could remain constant. General relativity then gives it an unusual gravitational role. Ordinary matter has positive energy density and pressure that is usually small compared with that density. Radiation has positive pressure. Vacuum energy, by contrast, behaves as if it possesses negative pressure, a tension built into space. In the equations governing cosmic expansion, pressure contributes to gravity alongside energy density. Sufficiently negative pressure changes the sign of the large-scale effect. Instead of helping gravity slow the expansion, it drives acceleration. This connection is elegant. The quantum vacuum supplies a physical source, while Einstein's cosmological constant supplies the mathematical form. They seem to fit together almost perfectly. Yet when physicists try to calculate the amount of vacuum energy, the elegance collapses into one of the greatest mismatches in science. Quantum field theory treats each field as a collection of possible vibrations. Even in its lowest state, each mode retains a small amount of zero-point energy. There are modes of many wavelengths and energies, and when their contributions are added, the total grows rapidly. The calculation cannot simply continue without limit, because it would produce an infinite answer. Physicists therefore introduce a cutoff, an energy scale beyond which the current theory is not trusted. Even with a conservative cutoff based on known particle physics, the predicted vacuum energy is enormously larger than the dark energy density inferred from cosmology. If the calculation extends toward the scale where quantum gravity may become important, the difference can reach roughly 120 orders of magnitude. This means the theoretical value may exceed the observed value by a factor written as 1 followed by about 120 zeros. No ordinary correction can close such a gap. It is not a small disagreement between measurement and theory. It is a sign that something fundamental is missing. If the predicted vacuum energy gravitated in the straightforward way, the universe would behave nothing like the one observed. Space would accelerate so violently that galaxies, stars, and perhaps even atoms could never form. Instead, the actual cosmic acceleration is extremely gentle on local scales. Dark energy dominates the total energy budget only because matter has become thinly spread across an immense universe. Its density is tiny in any laboratory volume. The mystery is therefore not why vacuum energy is large, but why the effective value associated with cosmic expansion is so extraordinarily small while remaining different from zero. Several possibilities attempt to soften the problem. One suggests that positive and negative contributions from different fields cancel almost exactly. Fermion fields and boson fields can contribute with opposite signs, and a deeper symmetry might force a balance. Supersymmetry offers one such idea by pairing particles of matter with partner particles of force-like character. In a perfectly supersymmetric universe, the vacuum contributions could cancel, but supersymmetry, if it exists, must be broken at the energies seen today because the proposed partner particles do not share the same masses as known particles. Once the symmetry is broken, a large residual vacuum energy usually returns. The cancellation must still be adjusted with extraordinary precision. Another possibility is that the vacuum energy changes during cosmic history. The early universe may pass through phase transitions as fields settle into new states. The force that separates electromagnetism from the weak nuclear interaction, the formation of the Higgs field, and the confinement of quarks inside protons and neutrons all alter the structure of the vacuum. Each transition should shift its energy. Yet the final result remains very close to zero on particle scales. This suggests either an unknown mechanism repeatedly resets the vacuum, or the connection between vacuum energy and gravity is not understood. Some theories propose that gravity responds differently to vacuum energy than to ordinary matter. Perhaps a hidden constraint removes most of its gravitational effect. Perhaps space-time adjusts itself through additional fields. Perhaps the cosmological constant is not calculated from local quantum fluctuations in the simple way assumed. These approaches are mathematically difficult and have not produced a widely accepted solution. The problem persists because both sides of the conflict are successful. Quantum field theory predicts particle behavior with remarkable accuracy. General relativity explains gravity from the solar system to the expansion of the universe. Each theory works extremely well in its own domain. When vacuum energy connects them, their combined prediction fails by an almost unimaginable amount. Dark energy may therefore mark the boundary where two great descriptions of nature no longer fit together. The mismatch also raises the question of coincidence. Matter density decreases as the universe expands, while a true cosmological constant remains unchanged. In the distant past, matter dominates. In the distant future, vacuum energy dominates overwhelmingly. Yet in the present cosmic era, the two densities are of the same broad order. There is no obvious reason for observers to exist near the transition between them. This is called the coincidence problem. It may be accidental, or it may hint that dark energy evolves with time. A changing field, sometimes called quintessence, could roll slowly through an energy landscape, producing negative pressure without remaining perfectly constant. Its density might track matter for part of cosmic history before becoming dominant. Such fields are possible in theory, but they introduce their own puzzles. They must remain extraordinarily light, avoid interactions that experiments would have detected, and evolve slowly enough to match observations. So far, measurements are consistent with a cosmological constant and have not confirmed variation. Another line of thought turns to the possibility of many universes or many regions with different vacuum energies in such a landscape. Most values would produce universes unable to form galaxies. Only regions with a small enough cosmological constant would allow matter to gather and long-lived structures to arise. Observers would naturally find themselves in one of those rare regions. This anthropic reasoning does not calculate the value from a deeper law, but it attempts to explain why a small value is observed. It remains controversial because it is difficult to test, and may shift the question from physical mechanism to statistical selection. Still, the extreme smallness of dark energy keeps the idea in discussion. Observations continue to refine the issue. Supernovae trace expansion across time. Baryon acoustic oscillations provide a standard ruler in the distribution of galaxies. The cosmic microwave background anchors the early universe. Weak lensing and galaxy clustering show how structure grows under the competing influence of matter and acceleration. These measurements constrain the equation of state of dark energy, a relation between its pressure and density. A cosmological constant has a particular constant value. Any measured departure could suggest a dynamic field or a failure of general relativity on cosmic scales. The current picture remains close to Einstein's constant, but the uncertainty is not yet zero. Empty space, therefore, stands at the center of the mystery. It may contain the energy that drives the universe apart, yet the best quantum calculations assign it far too much. The vacuum is known to be physically active, but its gravitational weight is unknown. It is measured as almost nothing and inferred as most of the cosmos. Between these statements lies a gap wider than any physical distance. The darkness accelerating the galaxies may arise from the quietest possible state of nature, but that quiet state refuses to agree with the mathematics built to describe it. The simplest model of dark energy is also the most difficult to explain. A cosmological constant fits the broad expansion history of the universe, yet it offers no clear reason for its tiny value and no mechanism for its origin. This tension keeps other possibilities alive. Perhaps dark energy is not truly constant. Perhaps it changes slowly as the universe ages. Perhaps it exchanges energy with dark matter. Or perhaps neither dark matter nor dark energy is a substance at all, and the real problem lies in the theory of gravity used to interpret the observations. These ideas begin with the recognition that general relativity and the standard model remain incomplete when placed together. The unknown may sit in the contents of the universe, in the laws that govern those contents, or in both at once. One possibility replaces the cosmological constant with a dynamic field. A field has a value throughout space, like the electromagnetic field, though it may not interact with light. If such a field changes only very slowly, its energy can remain spread almost uniformly across the cosmos and produce negative pressure. This hypothetical form of dark energy is often called quintessence. Unlike a true cosmological constant, quintessence can evolve. Its density and pressure may shift over billions of years, altering the rate of cosmic acceleration. The idea is attractive because it turns an unexplained fixed number into a physical process. The universe may not simply possess a constant vacuum energy. It may be moving gradually through a deeper energy landscape. Yet this flexibility creates new difficulties. The field must be extraordinarily light so that it changes on cosmic rather than laboratory timescales. It must avoid producing forces between ordinary objects that experiments would already have detected. It must also begin with conditions that lead to the observed acceleration at roughly the present era. A field introduced to solve one coincidence can therefore produce several new ones. More unusual models allow dark energy pressure to behave in ways a cosmological constant cannot. Some predict that acceleration weakens in the future. Others allow it to grow stronger. If the effective pressure becomes sufficiently negative, the density of dark energy could increase as space expands. In an extreme future, expansion might eventually overcome the binding of clusters, galaxies, stars, and smaller systems. This scenario is sometimes called a big rip. It is mathematically possible in certain models, but current observations do not require it. Another family of ideas connects dark energy to the rapid expansion thought to occur in the earliest fraction of cosmic history. Inflation is proposed to explain why the observable universe is so smooth, why its geometry is close to flat, and how tiny primordial fluctuations are stretched into the seeds of later structure. The process is usually attributed to a field whose energy briefly dominates space and drives extraordinary acceleration. After inflation ends, that energy transforms into particles and radiation, allowing the hot early universe to begin. The resemblance to dark energy is difficult to ignore. In both cases, a smooth component with negative pressure accelerates expansion. Perhaps the present acceleration is a distant echo of the same underlying physics. Perhaps one field has two very different phases, one near the beginning and one in the late universe. Yet the energy scales are separated by an immense gulf, and no confirmed theory connects them. Dark matter and dark energy may also interact. In the standard model of cosmology, the two dark components affect one another only through gravity. Dark matter gathers into halos, while dark energy remains smooth and drives acceleration. But there is no proof that their relationship is so limited. They may exchange energy or momentum through a hidden force. Dark matter particles could slowly decay into dark energy, or a dark energy field could alter the effective mass of dark matter over time. Such interactions might help explain why the densities of the two components become comparable in the current era. They could also change the growth of galaxies and clusters, leaving subtle patterns in the cosmic web. The challenge is that almost any interaction must be weak enough to preserve successful predictions. The cosmic microwave background, cluster abundance, gravitational lensing, and galaxy motions all restrict how strongly the dark components can communicate. The possibility of a dark sector extends this idea further. Ordinary matter is not a single substance. It contains particles, forces, bound states, radiation, and complex structures. Dark matter may also belong to a hidden world with its own particles and forces. There could be dark versions of electromagnetism, dark atoms, or dark radiation that interacts very little with the visible universe. Some dark matter might collide with itself, cool, or form compact structures, while another part remains diffuse. Such a sector could be rich enough to solve several puzzles in galaxy formation, yet hidden enough to evade direct detection. A theory flexible enough to explain many outcomes can become difficult to disprove. Progress, therefore, depends on precise predictions that distinguish one model from another. The alternative is more radical. Perhaps the missing components are signs that gravity itself is being misread. General relativity has passed demanding tests in the solar system, around compact stars, and through gravitational waves. But dark matter and dark energy appear when the same equations are applied to galaxies, clusters, and the universe as a whole. It is possible that gravity behaves differently over such distances or under extremely weak accelerations. In that case, the extra pull attributed to dark matter and the large-scale acceleration attributed to dark energy might emerge from a deeper gravitational law. Modified Newtonian dynamics offers one example. It proposes that below a very small acceleration, the relation between force and motion changes. This adjustment can reproduce the flat rotation curves of many galaxies with striking economy. The observed distribution of ordinary matter often predicts the rotation pattern closely, suggesting a connection that remains important even within dark matter models. Yet modified dynamics struggles to account for all the evidence by itself. Galaxy clusters still appear to require additional unseen mass. The cosmic microwave background and the growth of the cosmic web are difficult to reproduce without a dark component. Relativistic extensions have been developed, but none has matched the full range of successes achieved by general relativity combined with cold dark matter and a cosmological constant. Other modified gravity theories change Einstein's equations more broadly. Some add new scalar or vector fields. Some alter how curvature responds to matter. Some allow gravity to weaken or strengthen across particular distances. These models can sometimes produce cosmic acceleration without vacuum energy. They may also change the speed at which structure grows or the way light is bent compared with the motion of matter. This distinction creates a powerful test. In general relativity, the same gravitational potentials govern lensing and large-scale motion in a specific relation. A modified theory may separate them. By comparing galaxy clustering with weak lensing, astronomers can test whether gravity behaves as expected. Gravitational waves add another constraint. Their speed and damping can exclude broad classes of modified theories. The observation that gravitational waves travel at essentially the same speed as light removes many once viable models. None of this means that Einstein's theory is secure in every regime. General relativity predicts singularities inside black holes, and at the beginning of classical cosmic history, places where the theory signals its own limits. It has not been successfully merged with quantum mechanics. A deeper theory of gravity almost certainly exists. The question is whether dark matter and dark energy are direct clues to that theory, or separate phenomena that the deeper theory must still include. At present, the standard cosmological model remains dominant because it explains a remarkable range of observations with a small set of assumptions. It reproduces the microwave background, the abundance of light elements, the growth of structure, gravitational lensing, galaxy clustering, and accelerated expansion. Its weakness is not that it fails broadly, but that its main ingredients remain unidentified. The alternatives often explain one mystery elegantly while creating tension elsewhere. A changing field can account for acceleration but requires extreme lightness. Modified gravity can fit galaxy rotation, but struggles with clusters in the early universe. Dark interactions can address cosmic coincidences, but must remain nearly invisible. New surveys measure expansion and structure with increasing precision. Any departure from a constant dark energy density, any mismatch between lensing and motion, or any unexpected behavior in small galaxies could guide the next step. The deepest possibility remains calm and unsettling. The darkness may be a new substance, a new force, a changing field, a hidden sector, or a sign that gravity has been only approximately understood. The universe offers only patterned stars moving too quickly, light bending too strongly, structures growing in particular ways, and space expanding faster with time. Somewhere beneath those patterns lies the distinction between missing matter and missing understanding. The future of the universe is written not only in the stars but in the space between them. Dark matter gathers, binds, and preserves structure, while dark energy acts across the largest distances, slowly widening the gaps between systems that are not held together by gravity. At the present epoch, galaxies still fill the observable cosmos in every direction, yet the expansion of space is accelerating. If dark energy remains a cosmological constant, this acceleration continues without weakening, and the distant universe becomes progressively less accessible. Galaxies outside the local group recede faster as the volume between them and the Milky Way grows. Their light is stretched to longer wavelengths, becoming redder, fainter, and more difficult to detect. Over immense spans of time, many cross a cosmic horizon, a boundary beyond which newly emitted light can never reach the region occupied by the Milky Way. Their images fade gradually, their clocks appear to slow, and their final light is diluted into darkness. Space itself expands so quickly that the separation grows faster than light can overcome. Even though no nearby object locally breaks the speed of light, the observable universe becomes smaller in terms of what remains connected, though space as a whole continues to expand. The local group is protected from this separation because its members are gravitationally bound. The Milky Way and Andromeda approach one another rather than recede with the general flow. Over several billion years, they are expected to merge into a larger galaxy, accompanied by smaller companions. Their stars rarely collide directly because the distances between stars are immense, but their orbits are reshaped, gas is compressed, and the separate disks lose their original forms. Dark matter halos merge as well, producing a deeper shared gravitational well. The future remnant becomes an island galaxy surrounded by a widening ocean of nearly empty space. Other galaxies that now belong to the local group remain tied to the same system, while more distant groups slip away beyond reach. After tens of billions of years, the night sky of any surviving world in this remnant could contain little evidence that a larger universe exists. Neighbouring clusters would have faded beyond detection. The expansion itself might become almost impossible to infer from direct observation, because the objects that once traced it would be gone from view. The cosmic microwave background, already cold and faint, would be stretched to wavelengths so long that it becomes extremely difficult to detect. Future astronomers could study stars, planets, black holes, and the local galaxy. Yet the evidence for the hot beginning and the vast population of distant galaxies might lie beyond their horizon. The universe would not only become darker, it would become harder to remember through observation. Dark matter remains important within the isolated remnant. Its halo continues to hold stars and stellar remnants long after bright star formation declines. Yet dark matter does not prevent every form of change. Gas supplies are gradually consumed or expelled. Massive stars die first, followed by stars of lower mass over far longer periods. New stars become rare as cold gas disappears. Red dwarfs, the smallest and longest-lived stars, continue shining for trillions of years, using their fuel with extraordinary efficiency. Eventually, even these stars fade. White dwarfs cool. Neutron stars remain as dense remnants, and black holes gather some of the remaining matter. The exact details of this deep future depend on physics that cannot yet be fully tested, including whether protons decay and how dark matter behaves over unimaginable timescales. If dark matter particles can annihilate with one another, the densest regions of halos may slowly lose mass through rare collisions. If they are perfectly stable and do not annihilate, dark halos may persist far longer. Their destiny is tied to the identity of particles that have not yet been detected. Dark energy determines the larger setting. A true cosmological constant maintains a constant energy density as space expands. Matter becomes increasingly dilute. Radiation loses energy, and the relative importance of dark energy grows. The expansion approaches a state in which distances between unbound locations increase exponentially. This future is often described as heat death. Though the phrase can suggest more drama than the process contains, it is not a fiery end. It is a gradual movement toward emptiness, uniformity, and exhaustion. Useful energy differences disappear. Stars cease to shine. Matter becomes thinly scattered or locked in remnants. Black holes may eventually evaporate through Hawking radiation over periods far beyond ordinary comprehension. Space remains, dark energy remains, and isolated particles move through an ever colder universe. This outcome is only the simplest projection. If dark energy changes with time, the future may differ. A field that weakens could allow acceleration to slow or even end. In some models, expansion might settle into a gentler pace. In others, dark energy could become negative and reverse the cosmic motion, drawing the universe toward collapse. If its density grows stronger as space expands, a more extreme fate becomes possible, with bound structures eventually pulled apart. Current observations do not establish any of these alternatives. They remain possibilities allowed by uncertain physics. The task of modern cosmology is therefore not only to measure how much dark energy exists, but to determine whether its behavior changes. The difference between an exact constant and a slowly evolving field may be very small in the present universe, yet over billions of years it decides the fate of every unbound structure. New observatories search for that difference by mapping enormous portions of the sky. Supernova surveys continue to trace the expansion history. Galaxy maps measure baryon acoustic oscillations, a preferred scale left by sound waves in the early cosmos. Weak gravitational lensing charts how matter is distributed and how structure grows. Galaxy clusters act as records of the competition between gravity and acceleration. The cosmic microwave background anchors the early conditions from which later structure develops. No single method is sufficient. Each contains uncertainties from instruments, astrophysical processes, and the modelling of galaxies. When several methods converge, the allowed behaviour of dark energy narrows. The same surveys also sharpen the map of dark matter. They measure halo shapes, the distribution of mass in clusters, the abundance of small galaxies, and the subtle lensing caused by filaments. Particle experiments continue below ground, in laboratories. And at colliders, telescopes search for radiation that might come from dark matter annihilation or decay. Gravitational wave observatories test compact dark objects and the behaviour of gravity under extreme conditions. The search stretches from subatomic distances to the largest scales in nature. The dark universe is approached from every direction because it refuses to reveal itself directly. The greatest uncertainty is whether dark matter and dark energy are two separate mysteries or two expressions of a deeper one. One shapes structure by attraction, the other reshapes the future through accelerated expansion. They seem opposite, yet together they account for almost everything in the cosmic inventory. Ordinary matter forms stars, planets, and living systems, but it contributes only a small fraction of the total. The visible universe is therefore a brief luminous pattern within a dominantly dark reality. This does not make the known world unimportant. It makes its conditions more remarkable. Galaxies form because dark matter provides gravitational wells. They remain observable across great distances because cosmic acceleration becomes dominant only after structure has time to grow. The present era lies between the bright beginning and the isolated future, when the universe is old enough for complexity but still young enough for distant light to arrive. As observations become more precise, the simplest model may continue to survive. Dark matter may remain cold and weakly interacting. Dark energy may remain indistinguishable from a cosmological constant. Such a result would deepen rather than remove the mystery, leaving physics with a successful description but no clear origin for its main ingredients. Or a small inconsistency may appear: a change in the expansion rate, a mismatch in the growth of structure, an unexpected halo pattern, or a particle signal repeated in more than one detector. A quiet deviation could open the next theory of the cosmos. Until then, the future continues along the path implied by present evidence. Distant galaxies recede, their light stretches, and the accessible universe slowly contracts toward a local island of matter. The darkness between galaxies grows wider, but it is not empty of meaning. It carries the influence of dark energy, the fading traces of vanished structures, and the unanswered question of what most of the universe truly is. The horizon moves outward in distance, yet inward in knowledge. Preserving a final calm mystery, the cosmos may reveal its history only for a limited time, while the forces shaping its destiny remain hidden.